Greetings, math fans. All right, so we are starting chapter 4. So this is chapter 4A, and it's day 1. All right, so the first thing I want to talk about is something called extrema. And extrema means extreme y values on the graph. Okay? And we're going to talk about two different kinds here. You have absolute extrema, which are, we're going to talk about an absolute maximum. So absolute max, which is basically, if you think of a y value, it's the highest point on the graph. And then we have our absolute minimum, which is our lowest point on the graph. All right, and then we have relative extrema. And so we have relative max, which is my brother's dog's name is Max, so I think of him as he's my relative max. It's very exciting. Okay, and this is my this is just a high point. Okay, so it's like a relative max. It's just a high. Could have a bunch of them. That's the deal. It's a high point or high. I have high point or high points. Okay, and then you have a relative minimum, which are low point points. Okay? Okay, let's do a nice graph here. All right, and so we kind of label a few things here. First of all, I'm going to put some dots in these locations. All right, so this guy right here, it's our lowest point, right? The one here, it's our lowest point. And this is, we're going to call this our relative. I'm going to use R for relative and A for absolute just to save a little time here. But it's a relative and an absolute minimum point. All right, because it is the lowest point, so it's the absolute minimum, but it's also a low point in the graph. All right, this point right here. Okay, that's the highest point. And so it's a relative and absolute maximum point. All right, and the rest of these guys, the rest of these bumps are, this is a relative max, this is a relative min, this is a relative max. Okay, we're going to talk about this in a little bit here. These are our endpoints. Okay, but let's talk about a couple things here. Let's go down, cursor down a little bit. So this is important stuff. Relative extrema, they are never at endpoints. Very important, math fans. Okay, they're never at endpoints, which of course is a closed interval. Okay, so these 2 points that I circled here, here, and here never can be relative extrema. They can be absolute extrema, but never relative. Okay, next thing is absolute extrema. Basically, if the highest or lowest point is not defined, which good example of that is a hole, right? Then there is no absolute max or min respectively. So in other words, if the highest point is not defined, there's no absolute max. If the lowest point is not defined, there's no minimum. Okay, so basically, if you have a bracket, which means includes the value, then you can have absolute extrema at that point. Okay, and if you have a parenthesis, then no absolute extrema at that point. Okay? All right, so let's look at some examples of graphs. So these are example graphs. Okay, the first one's going to look like this. And I want you guys, basically what we're going to do is we're looking for the absolute extrema and relative extrema, right? The first thing I want to point out here, math fans, is there is no absolute extrema. Because the highest point and the lowest point are not defined. They're open circles, which means they're just doesn't include that value, right? They're not defined. So this has no absolute extrema. This is like a bump. This is a high bump, high point here. So this is a relative max. Good old max. Okay, relative max, and this is a relative min. Okay, pretty easy. Okay, let's look at another graph here. Almost the same thing. This is a relative max. This is a relative min. And of course, our highest point now is defined, so this is an absolute max. But not a relative max, because relative maxes can't be at endpoints. And of course, then this has no absolute minimum point. Okay? So far, so good. Okay, let's keep going with a few more graphs here. What about this one? Okay, so what's this point right here? This is an absolute and a relative max. These go on to infinity, right? Okay, but they get closer and closer and closer to a value, so there is no absolute min. Okay, let's look at the next one here. And we're going to put an open circle there and an open circle there. So it doesn't matter, this is not defined here, but who cares? Okay, I'm looking at the highest point here, and so that makes that a absolute and relative max. This point right here is a relative min, and because this is the lowest point there, it has no absolute min. Okay, not bad. Okay, let's look at the next one here. All right, so the highest point here, this is again an absolute and a relative max. This is that's our lowest point, even though, again, I don't care if the endpoints are undefined. I'm looking for the absolute, the highest and lowest point. So this is going to be our absolute and relative minimum point. Okay, another graph here. All right, so what I want to do with this one, point out, is that first of all, these y values are the same. These y values are the same. All right, so if there's a basically I look at this point right here. Notice how there is a closed dot and an open dot here. They're the same value, so that basically that open dot or that closed dot fills in that open dot. So this value right here is my absolute and relative max. And in this case here, this is an absolute min, and there happen to be two absolute mins. So this is also a relative min. Okay? Because it just happens to have two of them because they're both defined. Okay, but again, you can't have a relative min or max at an endpoint. All right, and look at one more here. Okay, notice it's got arrows on here, so this has no absolute max, and this has no absolute minimum. All right, of course it has a relative min, and it has a relative max. Okay, something called the extreme value theorem is if f is continuous on a closed interval a comma b, okay, of course with brackets, then f has both a max and a min value on the interval. Okay, which kind of makes sense. If it's continuous and it's got brackets, you've got a maximum minimum. Okay, when I say a maximum minimum, I'm referring to an absolute max and absolute min. Okay, I mean, just to show you an example here, right here, I'm just going to put two dots here, and it could be anywhere in here, right? I could say it could look like this. You've got a minimum value and you've got a maximum value. You're always going to have one, as opposed to some of these other examples where you have if it's not a bracket, if it's a parenthesis, that could be undefined at that value, and then you wouldn't have a max or a min, right? All right, so let's talk a little bit about relative extrema. We're going to be talking about derivatives now, which we're all so familiar with last chapter, right? So what can you guys tell me about this point and this point? What can you tell me with the derivative? Well, you guys remember derivative means slope of the tangent line. So if I draw a tangent line here, and I draw a tangent line here, what can you tell me about the slopes? Well, of course, the slope equals 0, and slope equals 0. It's equal to 0 in both places, right? So when the slope equals 0, which of course is a horizontal tangent, we get f prime of x equals 0, right? The first derivative equals 0. And if that's true, you have a candidate for a relative extrema. Okay, a candidate. And these candidates are called critical points. Okay, so far so good? All right. What about when the derivative is undefined? Okay, when the derivative is undefined. Okay, could that be a maximum or minimum point? That's kind of interesting. Think about that one for a second. When a derivative is undefined, when it's 0, we have a maximum and we have a minimum, of course, because we have a slope of 0. But what about when it's undefined? Okay, a lot of people say, well, no, you can't. If it's undefined, you can't have a maximum and minimum. Well, maybe. Let's check this out. Do you recognize this? What is that? It's a cusp. What's this point? Oh, it's a minimum point. That's interesting. And actually for this one, it's a relative and an absolute minimum, isn't it? Just looking at the function. It's very interesting. Okay, what about this one? Ah, very interesting. What is this? It's a corner. So again, this is a relative and absolute minimum point. So it looks like when it's undefined, it can be a max or a min, right? Okay, that's pretty good. So let's write some rules down here for relative extrema. So rules for relative extrema. Okay, the first is the function must be continuous at the point. Okay, and again, we're talking about relative extrema. And the second rule is the function must be defined at the point. Okay, when I refer to the function, math fans, I'm referring to f of x, not f prime of x. That's important. Okay, so let's look at two graphs here. I have this and this. Okay, this is not a relative minimum point. It is an absolute. It is an absolute minimum. Right? It's the lowest point, and it's defined. That's good. But it can't be a relative because it's not continuous at that value. Okay, it's not continuous. And let's do one more here. How about this? We'll put a hole. This is an open dot. Okay, this is not a relative or absolute max. Okay, first of all, it's not continuous. Right? It's not continuous or defined, right? It's not continuous at that point, and it's not defined. So that's why that is not a relative max, and it's not an absolute because it's a whole, right? It's got to be defined at the point in order to be an absolute extrema. Okay, so real quickly what I'll say here is absolute extrema. This is huge, math fans. You want to look at y values of all relative extrema. Right? You always want to look at all the y values of all the relative extrema and endpoints. I can't stress this enough. You've got to, if I give you a closed interval, math fans, you've got to look at the endpoints. You've got to plug values back in, because that's really how you look at endpoints. You're looking at the biggest y values. So you're going to plug in the x value endpoints to find out what the y values are. And I'm going to put on here, this is what I have in my notes, kids, forget this. Okay, I asked for absolute extrema, and kids plug in the relative x values and find out the y values, and then they get their values. They get, tell me what the absolute extrema are, and they totally forget to plug in the endpoints. Okay, you've got to test endpoints. Obviously, if it's an open interval, then there's nothing to test on the endpoint. If it's a closed interval, you've got to test the endpoints. It's huge, huge, huge. All right, let's start out with an example now, math fans. And just kind of get the hang of all this. So our first example is f of x is equal to x squared plus 4x plus 3. And x is between 0 and 5. Okay, before you want to start this problem out, I want you guys to think a little bit about what this is going to look like. What kind of results are you going to have? Okay, so I even wrote here, think about the graph first. Okay, it's going to be something like, do you guys agree? It's a parabola. Something like that, right? I don't know what the vertex is. I may could figure it out, but it's going to be a parabola. So it will have a relative and an absolute minimum value. Right? Right here. Right? It's going to be an absolute and it's going to be relative. All right, so let's actually do it mathematically. F prime of x, so we're going to take the first derivative, is 2x plus 4. What you're going to do with that is you're going to set it equal to 0 because you're setting the slope of the tangent line equal to 0. So 2x plus 4 equals 0. Solve for x, I get x equals negative 2. So this is it's a critical value, and it's a candidate for relative extrema. That's all we're doing right now, just relative. Absolute is kind of at the end after we find our relative extrema. Then we check out endpoints and test things out, okay? But anyway, that x equals negative 2 is our critical value. It's a candidate for relative extrema. All right, so now what we're going to do with that is we're going to do something called interval testing, which you guys are somewhat familiar with. Interval testing. And this is the way I want you guys to set it up here. This 2, or this negative 2 is right there, and we're going to pick points on either side. So we're going to pick negative 3, and we're going to pick negative 1. All right, literally what I'm doing is I want to test out, we know that my slope is 0 for x equals 2. I want to know what's going on at negative 3 and negative 1. So what we're going to do is, this is huge, math fans, we're going to plug negative 3 and negative 1 into f prime of x, because I want to know what the slope is at those points. Okay, so if I do f prime of negative 3, I get 2 times negative 3 plus 4, which is negative 2. And f prime of negative 1 equals 2 times negative 1 plus 4 equals positive 2. So math fans, the only thing, I'm going to put a positive here in front of it. The only thing I'm really concerned about, I'm concerned about the signs. All right, so what I'm going to do is I'm going to take that negative sign at negative 3, and that goes right here. And I'm going to take this positive sign, so that was the negative side, and then I'm going to take this positive sign, I'm going to put that over here. So this is what my interval testing is telling me. It's telling me at negative 3, it's a negative slope. Of course, at negative 2, we already know the slope is 0. And at negative 1, it's a positive slope. So I'm going to move this down and just show you what I'm talking about now. So do you guys agree, if I have a negative slope, isn't this a negative slope this way? And then so it's going from a negative slope to a positive slope. So negative slope to a positive slope. What does that make that? Makes it a minimum point. Okay, so that's how you're going to tell it. Just take your hand. Take your hand in the air and go negative to a positive. Oh, that makes a minimum. And that's what you have to remember here. So this guy right here, that negative 2, it is a relative minimum point. Okay? It's a relative minimum. Now the only way that could not be a relative minimum, possibly, is if I plugged it back into the original function and it wasn't defined. If it wasn't defined, then it couldn't be a candidate, right? You can't have a value that's not even defined in the original graph. All right, so in this case here, my relative minimum, which actually, look at this, we kind of proved it, didn't we say in the originally in the problem that a minimum value, or it's going to have a minimum value because it's a parabola opening up? Well, sure enough, there it is. There's our relative minimum. Okay, relative minimum is -2. All right, so I'm going to make a little modification of this problem in a second here. Okay, and the reason I want to make a little modification is this guy right here. We got all excited. We found our absolute minimum point. But I want you guys to understand, the reason I want to make this little modification is that's -2. That's not even in our range or in our domain, is it? Okay? It's not in our domain because our domain is from 0 to 5. So I'm going to actually make a little modification so this problem can work out because I want to kind of prove a point here. And I want you guys to change this from 0 to -3. Okay? And then let's continue on with the problem here. All right. So anyway, back to what we have here though. -2 is a relative minimum point. And what I want to do is, first of all, it's a -2 is a relative minimum x coordinate. Okay, I need a point for my relative minimum point. And guys, as you already know, what do with that? You plug it back into the original problem. So it's really f of -2. If I plug that in, it's saying -2 squared plus 4 times -2 plus 3. So f of -2 gives me -1. So my coordinate is -2, -1. That is my relative minimum. Now, these are some words that you guys need to know. It's on the bottom of your assignment sheet, but we're going to do it one time here so you actually see what's going on here. But let's look at a couple things again. Again, it goes from negative to positive. So that's what makes it a negative, or a minimum value, minimum relative minimum. Okay, so these are exact words that I'm going to have you guys use. And the reason I'm teaching this is because this is what the AP people are going to be looking for. So exact words. So f of x has a relative minimum at -2, -1, since f prime of x is equal to 0 and f prime of x is changing from negative to positive at x equals -2. Okay? So exactly what this says here, it says, first of all, I'm telling you it has a relative minimum at that point since the first derivative is 0, and it's changing, the first derivative is changing from negative to positive at x equals 2. All right? So this is what you're doing, is you're telling me you have a critical point here, and then you're telling me what the slope is from here to here. It's changing from negative to positive. That means it's a relative minimum point. Okay? That's the words you're looking for. Now here's the second part of the problem. It's kind of a big problem, but it goes faster because we're just learning the first part here. I want to look for absolute extrema. So we have, really in this problem, math fans, we have 3 candidates for this. Okay, I'm going to highlight this. The one candidate is on top here. We said it says from -3 to 5. So we have -3 here. We have 5. And so we have, let's just write that. We have x equals -3. We have x equals 5. And then, of course, we have x equals -2. That was our relative minimum. Well, again, we kind of know the graph is going to look like this, but let's just check out the endpoints. So really, since that's our only relative min, we kind of have an idea what's going on. We know that's going to be an absolute min, but let's just write this down. We have -2, -1, and then we're going to check our endpoints. So this guy and this guy right here. So remember, we're plugging it into the original function. So f of -3 is saying -3 squared plus 4 times -3 plus 3. So f of -3 is equal to 0. So our coordinate is -3, 0. And then f of 5, if you plug that in, we get 48. So it's 5, 48. And remember, math hands, we're looking for the y values. Okay, we're looking for the y values. So I have this y value, this y value, and this y value. So guys, it makes sense, doesn't it? That's our minimum, so that better be the lowest. So this actually is our absolute minimum point. And what's our absolute max? This guy right here. Absolute max. Okay, that's it. If this was not between -3 and 5, it was just a function, it would have no absolute max. It would just have an absolute min, which happens to be the same as the relative min. Okay, so again, but we're looking at y values. We're looking at that y value, that y value, and that y value. We're plugging in the x value, we're looking at the y value to determine whether we have absolute, max, or min. Okay? All right, so I got a few more examples to do with you guys. It goes a little bit faster. This is kind of long right now, but it does go a little bit faster. So let's take a look at some things here. Okay, so f of x is equal to x cubed minus 3x squared minus 9x plus 12. All right, and I want you to find the relative extrema. So we're going to do f prime of x equals 3x squared minus 6x minus 9. So that equals 0. I can factor 3 out. I get x squared minus 2x minus 3 equals 0. So I factor that to x minus 3, x plus 1. So my critical points are 3 and -1. Those are candidates, okay, for relative extrema. So let's do our interval testing. Got 2. I always like to make the long lines here. So we have -1 and 3, and pick points on either side. So -2, 0 is a favorite number, and 4. Again, I don't care what the number is. I'm going to do it first here, though. F prime of -2 is positive 15. F prime of 0 is -9. And f prime of 4 is positive 15. So again, I don't care what the numbers. I'm just going to write this in there, though. So take your hand, go up and down. That's what I'm talking about. Go up, positive slope. Go down, negative slope. That means this must be a maximum point. Okay, let's go to the next one. Going down to up. That means this next point must be a minimum point. Okay, and of course it's defined that value, so I'm good to go. And what I have here is, let's remember when I plug in, or I find the coordinates, f of -1, plugging into the original equation. So f of -1 is 17. So my maximum, my relative max is -1, 17. And my minimum is f of 3, plugged in the original equation again, is equal to -15. Okay, so that's going to be 3, -15. So here are your words that you're going to use. You're going to say f of x has a relative minimum at 3, -15 since f prime of x equals 0 and f prime of x is changing from negative to positive at x equals 3. Okay, pretty easy. Okay, and then the other one is f of x has a relative max at negative 1 comma 17, since f prime of x equals 0 and f prime of x is changing from positive to negative at x equals negative 1. Whew. It's x equals negative 1. Okay? So that's, again, that's it. If I look at the problem here, let's just look, see our slopes. If I make a quick graph of this, what it's probably going to look like, because the slope is positive to negative to positive. It's going to look, I mean, it's not the right coordinates, but it's probably going to look something like that. And think about it, it's a cubic. So cubic does look like that, doesn't it? And if I asked you for absolute max and min, what would you tell me? It has none, because this goes on to negative infinity, this goes on to positive infinity, so it has no absolute max or min. Okay? Got a couple more examples I want to do with you guys. All right. F of x is equal to x to the fourth minus 4x cubed. So the derivative, f prime of x, is equal to 4x cubed minus 12x squared. So we set that equal to 0 and factor out a 4x squared, and we get x minus 3 equals 0. So x equals 0 and x equals 3. Again, these are our candidates. Okay, so if I do my interval testing, and guys, remember, when you do your interval testing, you're plugging into f prime of x. That's huge, because I'm looking for the slope. I'm not looking for the actual values around it. I'm looking for the slope. So we have 0 and 3. And if we plug in our values into the derivative equation, again, I'm just going to put the signs here, but we get negative. Oh, I guess I picked negative 1, and I picked 1, and I picked 4. So if I plug that into my first derivative, I get negative. I get a negative, another negative, and then I get a positive. Okay? So that means this guy right here is not a max or min, okay, because it's a negative negative. So that's a candidate, but it doesn't turn out to be one. It's not a relative extrema. This, on the other hand, is a relative extrema. It goes from, take your hand, go negative to positive. It's a relative minimum. Relative min. Okay? So, and if that coordinate, plugging it again back into f of x, so f of 3 is equal to negative 27. And so we get 3 comma negative 27 for a coordinate. So we're going to say, okay, then we use our exact words here. I'm going to say f of x has a relative min at 3 comma negative 27, since f prime of 3 is equal to 0 and f of x is changing or f prime of x is changing from negative to positive at x equals 3. Okay, so those are the words I'm looking for, and we're done with the problem. See, it's going a lot faster once we've done a few of the problems. It's really not that bad. All right, I got one more. This is actually one of your homework problems, but it's a really good problem, and I like to do it with you just because it's got some interesting things here. So this is, like I said, it's a homework problem. All right, so f of x equals 1 over x plus natural log of x. And you are given endpoints as well. And basically you're given it's between 0.5 and 4. Okay, so including those points. And let's do the first derivative here. So you can use the quotient rule, that's fine. Bottom times derivative of the top, which is 0, minus the top times derivative of the bottom, so it's negative 1 all over the bottom squared, plus 1 over x. All right. We're going to find our critical points. And basically, you're going to set the first derivative equal to 0. It's a little scary. It's negative 1 over x squared plus 1 over x equals 0. Well, guys, you really, you could get a common denominator, or we could just move 1 to one side and 1 to the other, right? So can't we just say 1 over x squared equals 1 over x? Cross multiply, and we get x squared equals x. Move that x over, factor that out. So we get x equals 0, x equals 1. Okay? Yeah, it's a little weird, but those are our candidates. Okay, so we could start off by doing interval testing, but one thing I want to show you guys is that this guy right here, I'm going to highlight this guy right here, it's a critical point, but it's not really a candidate, is it? The reason it's not is because if you look here, this guy right here, actually both of them, if you plug in 0, 1 over 0, it's undefined. Natural log of 0 is actually undefined as well. Okay, so that's not something I'm even going to test, because that is not one of my, it's not one of my values, one of my absolute or my relative extrema. Okay, I know that. So the only thing I'm going to check here is I'm going to just check the 1. And remember, I'm plugging it into f prime of x. So if I plug that in, I get, well, let's put values on either side. Obviously, you can't pick 0, so we're going to pick 0.75, and I'm going to pick 2. And remember, I'm plugging into f prime of x, and if I do that, I get a negative value, and I get a positive value. So that means this kind, take your hand, go down to up. This is a relative minimum. And if I plug that into the original equation, so f of 1, so 1 over 1 plus natural log of 1, okay, that gives me 1 plus 0, which is 1. So my coordinate is 1, 1. That's a relative min. All right? But I did want to show you where it, you had an issue with that value of 0. It's actually not defined, so you can't use it. So here we go. We're going to say f of x has a relative minimum at 1, 1, since f prime of 1 equals 0, and f prime of x is changing from negative to positive at x equals 1. Okay? Before I end this lesson, which is actually a very long lesson, but before I end this, I want to say a couple things. First of all, the textbook does a few things that are different. It tells you that relative extrema occur at endpoints. Our class, relative extrema never occur at endpoints. And some of you guys are saying, well, why does the book say that and you say not? Well, I'll tell you, it's one of the things that they kind of stay away from on the AP exam, because some people say it does occur, some people say it doesn't occur. Personally, we don't know what happened. Remember, in order to have a relative extrema, the derivative has to be 0. Well, if it's an endpoint, what goes on the other side? We don't know. We have no idea what goes on the other side. We don't know. Here's an example, right? If it looks like this and there's an endpoint, is this going to go up after that? Is it going to go down? I don't know. If it's going to go up, it's not an extrema. If it's going down, it is an extrema. So we don't have a relative extrema at endpoints. We're not going to use that. They're not going to question that on the AP exam. If they do, either one is going to be correct. All right? And also, another thing for textbook, they use a word called, instead of relative, they use local. And when they refer to a max they're really referring to the absolute max. Okay, they'll actually say local if they're referring to a relative extrema versus, hey, just give me the max or give me the min. Okay? So that was, again, it was kind of a long lesson, but that's it, math fans. That's it, everything for just knowing a little bit about, relative extrema, absolute extrema, and how to find them. All right? Have a great day, math fans. Adios. Goodbye.